That's my room. All right. Anyways, a few weeks back, I was sitting in my room preparing for an English literature exam assignment, and I had to write an essay, okay, on badgers, right? So I started writing a few sentences, but I don't know enough about badgers to write a meaningful essay, and I didn't have any resources at home. But what I do know, I have a library 20 minutes away, right, which has books, and where I can find a book on badgers, right? So this is a big encyclopedia on badgers, supposedly. And I can make my way to the library, right, find this book, go to the page on badgers, find the first fact I can find, go back home and write a few sentences. But that's not enough to complete the essay. I need more facts. So I go back to the library, read another sentence, come back, and then write a little more. And I keep doing this a few more times. And I finish the assignment one eternity later, right? Now you might be thinking, that's a stupid way to do this, right? That's not a smart way to do this. Why don't I just go to the library, pick up the book and bring it home and then just use it there, right? I don't have to spend 40 minutes in this round trip. Well, then I'll say, look at the size of that book, right? And look at the size of state of my room. There's no way I can fit this book in that room. So you might say, well, you can still do better, right? There's probably some smarter way to do this. And there actually is. So what you can do, I could go to the library, I can find the book, I could find the page I'm interested in. I could make a copy of it, right? And then take the copy, like just a few pages, and take them to my room and put them on my bookshelf. And then that way, if I have to look up a new fact, I just go to my bookshelf, and it takes me like 10 seconds to do that instead of 20 minutes. And that way I can do this process much faster. And if that's sort of your approach to solve this problem, well, then I congratulate you, because that's exactly, you invented buffers, right? That's what a buffer does. So, except in a real computer, you have, the room is not your room. It's actually the CPU where all the processing happens, where all the real work happens. And your CPU has to get information from something called your hard disk, right? And it generally takes a long time for your CPU to get information from the hard disk. This big database, or this big book in this library, it's actually the database on your disk, right, which contains all the information about badgers or whatever else. And then to speed up everything, instead of talking to the disk every time and then spending a whole bunch of time in that process, you can make copies of portions of this database, just like we were doing, and then put them in a place which is closer to the CPU than the disk. And that place is your RAM, or your main memory, right? So you take chunks of the database that you need and put them in main memory, and then sort of access them much faster. And the timings are obviously off. So in reality, it takes about 10 milliseconds. Hold on. Okay. So in reality, for your CPU to exchange information between the disk and the CPU, it takes about 10 milliseconds. And the amount of time it takes to exchange data between your main memory, or your RAM and CPU, it's about 100 nanoseconds, which is about 100,000 times faster. So you might think, it's just a difference of a few milliseconds, what's the big deal? But when you think about a big server like Google server or Amazon server, when you save a few milliseconds of millions or trillions of queries, essentially, over a long period of time, you're saving a lot of time in aggregate, right? So this is a good thing. And to just sort of drive this example a little more, if the ratio of the differences in exchanging data was similar in my example, if it takes 10 seconds to read the page from my bookshelf, it would take 12 days to go to the library, right, if the difference was the 100,000x difference that is present in real computers. And all of this sort of ties into this concept of the memory hierarchy in computer systems, right? All of this works because we have different forms of storing data. Some are faster than the others, and some are cheaper than the others, right? So you have something like the disk, which is generally a very cheaper mode of storage, and you can have disks of 1 terabyte, 2 terabyte more, right? And then you have RAM, which is generally much more concise. You have in your computers, you might have a RAM of 8 GB or 16 GB or so. And then you have faster modes of memory, like the cache, right, which we won't discuss too much. So one natural question is that instead of talking to the disk at all, why do we have to spend that time doing that? Why don't we put the entire database on RAM, right, in main memory? And the problem is the one that we already discussed. The book is too big for the bookshelf, right? The same way, our databases generally will be hundreds of GBs, and your RAM is like a few gigabytes at max. So you can't fit the entire database in RAM. That's one big problem. And even if let's say your database is small, let's say it's just 1 GB, it's not too big. But even then, a lot of programs need this main memory to run their processes, right? So there's a lot of contention of this main memory. And as you can see here, this is a screenshot of the process manager on Windows. You see that a lot of programs are using main memory up, and almost 70% of it's used up. So if you have a database running on top of this, you have even lesser space to use for your database-related operations. Especially with modern computer systems and modern programs, you have like softwares like Chrome, which will hog up entire memory, chips without even blinking an eye. So we need something else. We need to store the database on disk and then only use RAM when we need it, right? Another sort of consequence of, or the difference, there's other differences in these storage media. In particular, RAM is something called a volatile memory. So if you disconnect it from power or you turn off your computer, anything stored in RAM gets erased, and you don't want your database to be erased, right? So even if you could fit your database in memory, if you turn your RAM off or your computer off, it just erases the entire database. So that's why we have this nice sort of structure. You place the database on disk, right, as a normal file or as a set of files. And then when you have to use sort of portions of that database, you just copy them into RAM, and that's where you use them. So giving a more concrete example, so imagine this big database on the red side, which is your disk, and you have main memory over there. What we will do is, instead of taking the whole database over, we will actually divide the database into chunks, and these chunks are called pages, okay? This is a general concept in operating systems, that you divide bigger files into these more manageable sections called pages, which act as units of transfer so that you can send a few pages to main memory and then sort of swap them in and out. So let's imagine you have a table, or imagine you have a database with a single table in it, and this is some data in that database. So what you'll do is, to represent this in your disk or store this in your disk, you will create a file, right, and you will divide that file up into these pages, and you'll decide what is the maximum amount of data I want to keep in one page. You can set this, based on some reasonable guess. You can set it like 4 KB or 8 KB. That's the general sizes of most pages. But in this case, the data is too small to like have 4 KB pages. It'll all fit into one page. So let's imagine that we set the limit as 4 rows per page. I can't have more than 4 rows in one page, okay? So what I'll do is I'll split up my sort of data into these sections, not more than 4 rows per section, and then I'll just divide them up into the pages that I've created. And then that gets stored on your database on file or on disk. On the other side, you have main memory, and you need to prepare main memory so that it can sort of swap in and out these pages. So we create this thing called a buffer pool in main memory, which is essentially an array, right? It is an array which can store pages from disk, right? And the buffer pool has a number of frames, right? You can decide what the size of your buffer pool is. In this case, there are n frames. And each frame can host or store exactly one page, right? So one page goes into one frame. The size of the frame and the page have to be exactly the same. So you have a bunch of pages on your database. Let's imagine you have 100,000 pages because your database is pretty big. And when you run a query in SQL or in some database processing system, you will only be interacting with a few of those pages at a given point in time. So what you'll do is you'll go to the database on disk, you'll figure out which pages you're interacting with, and you'll just copy them over to your buffer pool, right? And that way, when you have to reuse data from those pages, it's available in a much faster, much closer sort of location in your system. Now, a question that you might have here is, let's say I'm running a query which only updates or which only reads one row from my table, right, from this table, right? So let's say I'm just interested in the very first row, the Albert Einstein row. Why do I need to like pull up the whole page surrounding it, like the rows before and after it, into the page and then sort of load all of that into main memory? So the reason that we do this is because of something called locality of reference. And locality of reference is this general idea in computers which says it's very likely that you will use something that you recently used again in your program. So if you use, let's say, a few rows at some point in your program, it's very likely that a few statements later that you will reuse those same rows. And not just the same rows, it's quite likely that you'll use the data surrounding that set of rows. And this is sort of a straightforward concept. Like imagine you have an array, right? So if you're iterating on the 10th element of the array, it's very likely that you will next iterate on the 11th and the 12th element. So it makes sense to load an entire page instead of just one row. And the locality of reference has sort of two aspects. There is locality of time, which means if I access an element at some point in time, it's very likely I'll access the same element at a time span that's very close to the first access, right? That's locality of time. And then there's locality of space, right? Which means that if I've accessed an element, it's very likely I'll access elements around that element, right? So a few rows before or a few rows after, it's very likely that I'll need those in my program or in my processing. So going back to our setup, so we have the pages on disk, right? We make copies of that page on main memory. And now once we have that, anytime I need to read or write any information, I'll do that on the page in memory, right? I won't go to the disk because that wastes a lot of time. So I'll just read and write everything on the page in memory. Now this creates a problem, right? So if you write something to this page, that doesn't reflect on disk yet, right? It's just written on the page in memory. And as we know, main memory is volatile, so you can easily delete this and lose all your progress. So what we do need to do essentially for such pages, these pages are called dirty pages. So if a page has a write which hasn't been synced to disk, that's a dirty page. So what we need to do occasionally is call a flush operation, which syncs the page between the memory and the disk. Now, as we saw, the main memory we have is limited, right? So the amount of pages that we can store in main memory is limited. And we have a lot of programs contending for that limited amount of main memory. So what happens when my buffer pool gets filled up with pages and I need to insert a new page? So I've already had like 100 pages inserted, and that's my buffer's capacity. But I need a new page now. How can I insert it into my main memory or in my buffer pool? So for that, we have different what we call eviction policies. So an eviction policy basically decides I need to kick some page out to make space for a new page, okay? And there's different ways to do this, right? You can do something like first in, first out. So the page that was inserted in main memory the earliest gets kicked out the first. You can do something like last in, first out, which makes less sense in this case, but you could do it, which means the page that was inserted the most recently gets kicked out the first, or a more recent or a more relevant, I guess, and a more useful approach is least recently used. So a page which hasn't been used for the longest time gets kicked out the first. In your project, you'll be implementing a much simpler algorithm called the clock algorithm. So it's simpler than the other three that we just talked about because you don't need to maintain any sort of complicated data structures to track which pages need to be kicked out. And how it works is pretty straightforward. So you have your buffer pool, right? So imagine you structure this buffer pool as a circular list, right? And you have this clock hand, okay, which points to one frame or one slot in that buffer pool at a given time. And anytime you need to find a new page, you'll check, is the frame that I'm currently pointing to, is it eligible for kicking out, right? Is it a good frame or is it a good frame to evict? If it is, then you will say, okay, this is the frame that you can use to insert the new page. If not, you'll move the clock hand forward and then sort of figure that out. So as an example, imagine this is your setup. You have a few frames. Some of them have been occupied by actual pages. And let's say a new page comes bouncing in, right? You need to make space for this. So what do? So you check, is the current position eligible for inserting this new page? Can I kick this page out? Let's say you can't because it's being used by something else. So you'll move the clock hand forward, and it points to the next slot, which is an empty slot. And then you'll sort of move this new page to this slot. Now we have this buffer pool. Everyone looks happy. And the problem now is the buffer pool is full, right? So let's say we have another page come in. Now I need to figure out where do I put this page. So the clock hand algorithm, what it does is that it checks, is the current location or is the current frame, does it have a page which I can kick out, right? Let's say the current frame does not have a page I can kick out. I move to the next position. I check, is this a page I can kick out? And let's say it does satisfy the condition, so I kick it out. And then I put my new page in there, right? Now, what is the condition based on which I kick this sad-looking page out? So there's two basic things. The first one is that no one was referencing that page, right? So, or no one has recently referenced that page. So let's say it was inserted like a few minutes ago, and then ever since, no one has come around and re-accessed that page. So it hasn't been accessed in a while. And the second thing is that there's no current users of that page. There's a difference between the two. So imagine that you're running a query, and the query is a long-running query. So it loads some pages up, and the query runs for let's say, 2 minutes. But it's very likely if that query needs some page, it'll need it at the end of that 2 minutes as well. So what that query will do is it will pin the page. And unless it manually unpins the page, no one can kick it out, okay? Because that query is still running, and it still might need that page. So if the page is not pinned, and if no one recently accessed it or referenced it, then you can kick the page out. And then you can make space for a new page to come in. So just as a concrete example, so imagine that there are 5 concurrent users of a given page. Then the pin count for that page will be 5. And as long as the pin count is greater than 0, you can't kick the page out. It has to be 0 for you to be able to kick it out, okay? All right, so that was a lot of theory about the buffer manager in general. I'll take a 2-minute break and let people ask any questions if there are any doubts, and let people digest everything we just discussed. Any questions about any of this? I might be doing a great job then. Okay. Right, so that was sort of the theory of the buffer manager. Now I'll talk a little more about the actual code that you'll be working on and sort of the classes you will see and the functions you will have to work with. Going back to our example of the mini rail burger, I mentioned that the first layer, the top layer, and the bottom layer, they're implemented. We will give them to you. So what do these layers do exactly? So the SQL parser layer, what it does is that it takes in SQL queries, right? SQL queries which look like select star from users. It figures out what it means, like what is this query supposed to do, right? It essentially converts it into an intermediate representation of the query. And in most databases, this intermediate representation is called a parse tree. So it's sort of split. This is not the same example. This is the wrong parse tree for this query, but I'm just sort of giving an example. But anyways, the SQL parser layer, it translates the query from the higher level programming language that we've written it in, and then translates it into a more lower level representation that the lower layers of your program can understand. The I/O layer, which is the lowermost layer of that burger, as I mentioned, it deals with creating files, reading files, opening files, things like that. And it also allows you to do things like create pages within a file, okay? And each page has a page number to identify it. So the I/O layer will have functions to create a file, open the file, read file, create pages in that file, and go to a page within the file, and things like that. This is what you'll be implementing, buff.c, buff standing for buffer manager, not the buff Pokemon there. But buffer manager, or the buff.c class, or the file has this class called the buff manager, buffmgr. And it has a few different methods, and these are the methods that you'll be actually implementing in this assignment, okay? The first one is called alloc buff, which essentially finds a new slot in your buffer manager to insert a new page. It just finds a slot. It doesn't actually insert the slot or insert a page in that slot. It just finds a slot. The second one is called the read page function, which allows you, as you can imagine, it allows you to read a page. If it's in the buffer manager, it will read from the buffer manager. If it's not in the buffer manager, it will actually get the page from disk, put it in the buffer manager, and then read it from there. The next one is the unpin page. As I mentioned, you can pin pages when you start working on them so that no one else kicks them out. But once you're done with your work, you can call this unpin page function, and that sort of reduces the pin count of that page so that it can be potentially kicked out. And the last function you'll work on is the alloc page. Alloc page is, as the name suggests, you're creating, or you're essentially creating a new page in disk so that you can write data on it. Okay, we'll talk about this in a little more detail in a second. So these are the sort of so buff manager is a class, so these are the methods of that class, these 4 methods. There might be some other methods, but you don't have to work on them necessarily. In addition to these methods, there are also some data members of this buff manager, so it tracks things about the buffer, the state of the buffer. One thing that it tracks is what is the size of my buffer pool, like what is the maximum size that this buffer pool can hold. And numbuffs is that field which stores that. So if numbuffs is 5, that means I can hold at max 5 pages in my buffer pool. So in this case, you have n frames, and therefore the numbuffs in this case will be n, which might be, let's say, I don't know, 10 or 100, whatever it is. Then you have another variable called the buff pool. If you look at this, if you worked with C or C++, this is actually a pointer to a page array in a sense. So this points to the actual buffer pool, because the buffer pool itself is just a sequence of pages, right? Some of them might have actual pages in them. Some of them might be like empty slots. But at the end of the day, it's just an array of pages. So that's what this buff pool variable represents. That's where it points to, the actual buffer pool in memory. You also have something called the buff table. So the buffer pool, it actually stores the pages themselves. It does not store any metadata about these pages, so things like the pin count and, was it recently referenced or not. That's not in the buff pool. For that, we have another thing called the buff table, right? And for each frame, it stores a bunch of metadata about that frame. So what does it store? This is the same slide, but a little more clear. So let's look at frame 1. For frame 1, it stores what is the frame number, which is 1. That's pretty straightforward. It stores a flag called valid, which means is there a page in this frame or not? So if there is a page, valid will be true. If valid is false, that means there is no page in the frame. you can essentially put a new page in if you want. You don't need to do anything else. If there is a frame or if there's a page in that frame, then the file field will be set. So it'll say which file does this page belong to. The page number will point to which page in that file does this frame, sort of store. Pin count, as I mentioned, is how many concurrent or active users of this page are there in the system. Ref bit is a bit indicating was this page or was the page in this frame accessed recently or not. If it was accessed recently, then you won't kick it out. If it wasn't accessed recently, you can kick it out. And finally, the dirty flag. So before you kick out a page, you need to check, is this a dirty page, which means does it have any changes which haven't been synced to disk? If there are any changes, you need to first sync them to disk, and only then do you get rid of the page, because otherwise you'll be deleting some changes that you made potentially. Clock hand, we already sort of discussed this briefly. So clock hand points to one of the frames in the buffer pool, and it checks, is this frame eligible for inserting a new page? And it runs the clock hand algorithm that we discussed. So in this case, if the clock hand is pointing to frame 0, the clock hand's variable will be 0. And then when you move it forward, it'll become 1 and 2 and so on. And it cycles back, right? It rotates around. So if you didn't find a valid insertion position or a valid frame in the first go, you can actually run it again to find maybe a new page or a new frame might now be eligible for inserting a new page. I don't know why I put this in, so I'll skip this. There's also a hash table. So this is just sort of an optimization thing. So imagine you have this task. You want to read page 10 in your file, and the file is called scientists.table. So one way you could do this is you can go to this buff desk array, right? And you can iterate over each element in this, and you'll see, oh, is the file scientists.table, and is the page number 10? If it is, then great, I found the page I want to read. If not, I'll move to the next one and so on. It's sort of a linear search, as you can imagine. It takes a bit of time. A faster way to do this is just create sort of a hash table which maps your file and page number to the frame that page is in, if the page exists in the buffer pool. So it maps your file and page to the frame number in the buffer pool where that page resides. So if you don't have a file and a page in this table, then that means the buffer pool does not have a page corresponding to that file and that page number. So you might need to insert it from disk. The last section of this presentation is basically the methods. I'll just quickly talk about like what at a high level they do. So allocbuff, as I mentioned, it finds a new slot to insert a page in. So imagine you have a buffer filled with some pages, some slots are empty, some slots are not. Some pages have been accessed recently, some pages are pinned. So this allocbuff runs the clock hand algorithm to sort of go through the buffer pool and identify which frame in the buffer pool can be used for a new page to insert, for a new page to be inserted in. As I said, it runs the clock hand algorithm. I think we already talked about that a few times. Now, one possibility is that what if my buffer pool is full, right, and I can't evict anything? Let's say every page is pinned. I cannot kick anything out, so what do I do then? How do I insert the new page? Well, in that case, you'll just throw an error saying that, oh, there is no space in the buffer pool, so whatever query is trying to get a new page inserted, they'll have to wait for a second. Also remember to flush your pages if they're dirty. You need to sync changes to disk. So before you kick out a page to insert a new page, you need to make sure that you call the flush operation, which I'm pretty sure is implemented in the I/O layer that we talked about. So make sure you call that so that the pages are synced and your changes are persisted. That was the first function, allocbuff. The next function is readPage. It basically finds the page either in the buffer manager or in the buffer pool, and then sort of returns its contents. If it's not in the buffer pool, it will go to disk, fetch that page, insert it into the buffer manager or in the buffer pool, and then sort of read the contents and return it back. Now this function, if you look closely at this signature of this function is a little weird, right? So when you want to read a page, you can imagine you want to provide, I want to read a page from XYZ file, and I want to read page number 10. Like, that's the first two arguments. The last argument is actually the output. This is a little strange. You might not see this in a lot of other programming languages. But we use the last argument as a pointer to the output, right? So once we find the page corresponding to the file and page number, we set its value or we set its contents in the last argument, which is a page pointer. And that way, whoever called this function, they also have access to that last variable. They can just use that as the returned value from this function. So there isn't an explicit returned type in this case or a returned object in this case. I think it just returns true or false depending on whether read page succeeded or not. But the actual page itself will be stored in this last variable called the page variable. quick question here. So, what was the question? Okay, yeah. So let's say you need to figure out, if the buffer pool has a page corresponding to a file and a page number. Which of these variables would you use to identify that? Any ideas? Is that a hand? No, that was a. Okay, never mind. Yes. Yes, exactly. Hash table, right? So you can also use the buff table, but as I mentioned, it'll sort of run a linear search over that thing to figure out whether that page is in the buffer pool or not. But the hash table is a much easier way to access it. So the read page function should use the hash table to figure out, oh, is this page in the buffer pool or not? If it is, then just set it in the page variable. If it's not there, go to disk and find it, right? So yeah, that's the same thing. Yeah, that's basically the same thing. So if you don't find the page in your buffer pool, then you need to go to disk and insert it from there. So that was that. Skipping these. Okay. Unpinned page, nothing much to discuss here. You're given a file and a page number. You check if it's in the buffer pool. If it is, you reduce its pin count by 1. That's all you need to do. Also, you need to check the, I don't remember exactly what you need to do with the dirty flag, but it's mentioned in the project description, so you can take a look at that. Last function, alloc page. So the reason we need alloc page is that imagine you have a page and you're writing to it, and you filled up the entire page. There's no more space to write. And now you still need to write more data. So what do you do? Because the pages have a limited capacity, right? They have a fixed size that they can accommodate. So if you need more space, you'll need to create a new page, essentially. And for that, you call the alloc page function, which does two things. It actually talks to the I/O layer and asks the I/O layer to create a new page for that file on disk. It'll be an empty page at this point because we haven't written anything to it. And after doing that, after creating the page on disk, it also, sort of creates a page in memory. Because if you're creating a new page, it's very likely you want to write something to it, so it doesn't make sense to just create it on disk and then fetch it later on. So you'll create the page on disk, also create the corresponding page in the buffer pool itself so that you can write to it, and then later on flush the changes back. So that is the two things that you need to do in this function, right? So alloc page will, first of all, create a page on disk, and then it'll run the alloc buff function, which was the first function, to find some space in the buffer pool to insert this new blank page, and then let you run any queries on it. So a quick sort of question here. So when we create this new page on disk, and then we also have a copy of it in the buffer pool, do we need to copy anything from the disk to the buffer pool, right? Because for other cases, when you had an existing page, you would need to go to disk, right? Find the page, copy its contents into your buffer pool. But in this case, you're creating a brand new page. So you'll create the page on disk. It'll be a blank page, and then you'll create enough space for that page on your buffer pool. But since there's nothing on the page on disk, you don't need to copy anything from disk to the buffer pool, right? So you don't need any sort of data transfer to happen between the disk and the main memory in this case. You can just create these two pages separately. Right, so now wrapping up, that's the gist of the assignment. You will be working in groups for this assignment, so the recommended sort of way to split this up, I would say, is first just sit together, discuss the pseudocode that you will write, sort of the logic that you will write for the different functions, make just rough notes of that, and then divide the 4 functions up. In a lot of cases, what people do is they'll be like, oh, I'll do function 1, you do function 2, and then we'll be done. But then there's no cross-communication. There's no communication between like, oh, what does function 1 do, and how do you implement it? So I would recommend at a high level, figure out the pseudocode for all the functions, and then split up work after that. Also, as I mentioned, the due date for this is after the spring break, so you get 4 weeks instead of 2 weeks for this. Again, none of this will be in your exam, in your midterm. It might be there in your final. And yeah, that's basically it. So I'll be here for questions if anyone has any. Yep. When should we call flush? Right, so going back, where is alloc buff? Right, so alloc buff, the question is, when we run alloc buff, when do we call flush page? Alloc buff finds a slot in your buffer pool which can be used for inserting a new page, right? And let's say it finds a slot which has a page in it already, which has some unsynced changes. Yes. So at the end of alloc buff, you should have essentially a frame ready for insertion, which means if you had to kick something out, make sure you sync the changes before you kick it out, okay? Mhm. So the ref bit, I don't know if I had it anywhere. So first of all, you will unpin the page only when the parent process requests that. You won't do it automatically. So someone has to call that. So whatever query was running in the upper layer, once it finishes, it'll call unpin page automatically. You don't have to like run it in the clock hand algorithm. There was also another point about, let me go back. Okay, so that was the pinned part of it, right? There's also the reference. No one recently referenced it. So the way that it works is that when you insert a new page in the buffer pool, you set its ref bit as 1 or true, which means it was recently just created or accessed, right? Or anytime someone uses it, you set its ref bit as 1. And when the clock hand algorithm runs, the first time it sees the ref bit as true, it doesn't kick that page out, but it unsets the ref bit. So that the next time it comes back around, it sees that, oh, okay, now it hasn't been accessed in a while, so I can kick it out, okay? The reference count is not really a count. The reference count is just a bit. It's a ref bit. So it's either true or false, which means it was either recently accessed or it wasn't recently accessed. And whenever it was accessed, you set it as true. And then you run the clock hand algorithm. It comes across such a page which has ref bit as true, which means it has recently been accessed. You don't kick the page out because it was recently accessed, but you will set, before moving the clock hand to the next position to check, you will set its ref bit as false, so that the next time the clock hand algorithm comes back, it sees that, oh, okay, I must have reset the bit recently because, I went over it once. So now it's fair to kick it out, okay? So, yeah. Right, any other questions? Okay, I guess that's all. You guys are free to go. Thank you for coming today.